Okay, so today for 10.2, we are doing translations. Okay, so we're going to define a translation, use component notation to describe translation vectors. So this is getting into like translation stuff that you've probably never really done before. And then we're going to perform some translations using a translation vector or a composition of reflections. And we're going to apply translations to solve real world or real life problems. All right, so the notes here, I have tried to clarify some of the stuff that the book has, but it is rather, the notes aren't necessarily super helpful, like the typed up stuff. So paying attention to the practice problems is going to be really helpful for today. But when we think of translations, you should think of chess, right? Because each of the pieces in chess has a different translation. Like you can go forward 1, and that's it. Or you can go forward 2 and left 1, like, or side to side 1, right? For the knight can do that. You can go diagonally across the board. Each of the chess pieces, whether it's the rook, the bishop, the knight, the pawn, has different moves it can make. Okay, but all of the moves are translations. They're just moving from side to side. Because a translation is that we're sliding a figure a fixed distance in a given direction. All right, so then we have this awesome diagram here of two triangles. Okay, so notice we have P1 or P and P prime. Okay, so it's original location and it's image, pre-image, and it's image. So a half arrow is used to name the vector from P to P prime. Okay, as vector P prime, or we can call it vector V. Okay, because the vector has the length, so this vector is the length from here to here. Okay, it has that length, but the vector also shows the direction. It has an arrow on it to show direction. So there's two different components to that we don't ever think about with an arrow, but in this case, but like it does. A vector shows us the direction and the length. Okay. Next up, vectors in the coordinate plane are typically described by their horizontal and vertical components. So you're going to see like your vector equals A comma B. That's an ordered pair, right? Is that A comma B? Isn't that an ordered pair? Okay. However, it's saying A is the same thing as x2 minus x1. So it's saying it's this coordinate minus this coordinate. Like, how did I get? What's the distance from here to here? If I need it. Okay. So this is the horizontal. A is the horizontal change that we're having. This one only has horizontal change. B tells us the difference in our y values. That's the vertical change or vertical movement. Okay, so if I had, like in this case right here, this vector is a diagonal, right? Okay, it has some slope to it, but we need to know its horizontal and its vertical change. So we would need to know what is this value, the change in x, which is equivalent to our A, and this value is the change in our y, which is equivalent to the B in our vector. Okay? Again, may not make a lot of sense just yet, but we'll make it make sense. All right, so this notation shows the movement. Okay, it shows the movement from the initial point P to the terminal point P prime. So a vector shows the movement. In a translation, all the pre-image points move. A units right and B units up. So again, A is horizontal, B is vertical. It could be left and down. Doesn't really matter. Then a translation described by the translation vector V, okay, equals AB. So that's what it's saying is it maps every single point P of the pre-image to the image P prime. So we're moving every single point in a shape. So this makes it sound like really confusing. I'm going to make it a lot simpler when we get there. Okay, so let's actually put it into practice. All right, so example 1. or example 2, pardon me, because I skipped example 1 from your notes. All right, it says describe the translation of the black parabola to its red image, which you can't really tell. The top one here is black. This one's more gray is the red. Then state the translation vector and the mapping rule. All right, so first of all, we're going to describe it. What happened from here, this point here, to this point here? Down what? 4. Okay, so it went down 4. Perfect. Did it go left or right at all? No. So we could write left/right is none. Or you could put 0. However you want to do that. Because now that we have our description, we can write the translation vector. So our vector equals, we need a coordinate, right? We need A. A is the horizontal change. How did it change horizontally? It didn't, so it's 0. B is the vertical change. How did it change vertically? 4. What else about 4, though? Why is it going to be negative 4? It's down 4, so it's negative 4. There you just wrote your vector. Vector, your vector for this one is 0, negative 4. So it seemed really complicated up above, right? Does it seem so complicated now? Not so much. Now, the part that might be a little complicated is this mapping rule. Okay? Yeah, right? So the mapping rule says, okay, I start with P at x, y. And I want to go to P prime. What happens to my x and my y? What happens to my x? What do I do to my x coordinate? Okay, I'm going to add 0 or I do nothing. You could put plus 0 or you could just leave it. I'm going to put plus 0 so you see where they're coming from. What do I do with my y coordinate? There's your mapping rule. And you're done. Okay, so again, like the note part, the way, like it's very wordy. I tried to kind of rephrase it, but keep theirs, and I'm like, it's just really complicated. I'll have to get better at that next year to rephrase it to make it sound a little simpler. But that's your mapping rule and your vector. Okay, so example 3 then says use vector v to translate ABCD. State the coordinates of the image's vertices and the distance each point is translated. And so you might be thinking like, man, this is a diagonal line. How on earth do I know how to translate it? It's down 1, right 2. We do the slope, but it's not down 1.
It's down 2, right 1.
Okay. Down 2, right 1. But we want to go to the end of it, right? So we're going to go, we could look at the slope. We went down 4. Okay, so negative 4. And right is a positive 2. But we need to write that. It would be helpful if we wrote that in that vector notation just so we could practice. What would our vector notation be? It's A comma B, right? A is what? Like, do we do our horizontal or our vertical first? Horizontal. So the vector notation is going to be
4.
No, horizontal.
Yes.
Horizontal. It's with the horizon. 2. And what's our vertical change?
4.
Negative 4. Good. All right, so that's all we're doing. With each of those points, we're going to move them 2 to the right. So I'm going to go to A, I'm going to go 2 right, and 4 down. 1. It is tremendously hard to see on this board. So 1, 2, 1, 2, 3, 4. Okay, is A prime. B, we go 2 right and 4 down. It is kind of small. C, we go 2 right and 4 down. and then D. 2 right and 4 down. I think that's
Mine looks like a turtle.
okay. So we need to state the coordinates. So what's the coordinate of A prime?
-2, -1.
-2, -1. Okay, Justice, what's the coordinate of B prime?
Nothing. Your yawn was funny. I don't know why.
-1.
No.
Yeah. Oh, do I go sideways first?
Mm-hmm.
Okay. Oh, 1.
There you go. Because we always do horizontal. Lucas, C prime.
Down first.
-1. Right now.
It'd be what?
Am I doing the second one?
You're doing
C
the
prime.
C prime.
Mm-hmm. Yeah, the second C. Yeah, the bottom one. Uh-huh.
So it would be 1 -2.
Correct. All right, and then Caden, back to you for D prime.
-1, -3.
Good.
You're supposed to do the vertical.
Okay. So we stated our coordinates after that. And then it says find the distance each point is translated.
4/2.
It is not 4/2. Okay, so if you think back to earlier when we've done geometry, we had a distance formula.
Oh no.
D
No,
equals
homie.
D equals what?
X1
X.
minus X2. Or is it Y?
No,
D equals the square root.
That's what I meant.
X1
X1
minus X2 plus
That's
Y1
Y1 minus
minus
Y2. That's the one thing I can remember. Like,
Was it like that?
yeah.
No.
No. Yes. Yes, it was.
That's not your distance formula.
What? Oh no. Aren't those in parentheses and squared? Both of them?
Yes. Yes, they are. Yes, they are. And now it's right.
You sure?
In a second, I will be. No. X2 is first, so that's Y2.
Okay.
Well, I write the whole thing down just to do that, okay?
You know, it'd be funny if we are right and she's just testing us.
It would be. I like that too. And I would do that.
You have done that before. I was writing a page
Okay.
for that.
So this is true. That's one way to find the distance. Okay. And that works great. Another way you can find the distance, however, so that's going to be your backup. Okay. Another way to find the distance is to use your Pythagorean theorem.
Yeah, let's do that one first.
Okay, so because we have our vector, right? And so our distance would be this side. So we have a side of -4 and 2, and we could find that distance. So we would say, all right, so here d squared equals my 2 sides squared. So -4 squared plus 2 squared. So d squared equals 16 plus 4. We'd have to take the square root, right? So what would d equal?
6. No.
Well, it's because it's square root of 20. I'll put that in there. So what is that?
5.
What's the square root of 4 times 5? Is that what you're saying?
No, 4.5.
No, that's not 4.5. Are you saying the answer is 4.5?
Yeah, somewhere between there.
It is.
I was close. I said 4.
Okay, so like if we look at it like this, which is helpful, we could take the square root of 4, which is 2. So then we have 2 on the outside, 2 times the square root of 5 here. which does equal 4.5 units. Interestingly enough. Okay, is our distance. But again, because our vector, like we have the distance and we're writing it with this vector notation, we can take those and set up a Pythagorean theorem to find the distance. Okay. So there's some weird stuff going on with translations that it's like, you know, in geometry we look at it from a totally different perspective than you've probably ever looked at translations before in like 6th, 7th, and 8th grade or earlier. All right, so then let's compare this to the one on the back. All right, so example 4 is the Blue Angels FA-18 Hornets are flying in a tight diamond formation.
Are the Angels or are the Hornets? 'Cause Hornets are
Neither one. Blue Angels is the group, and their planes are the Hornets, so they're technically Hornets. Blue Angels are the name of the people flying them. Okay, so they're flying in this tight diamond formation. We need to find the horizontal and vertical components of the translation that would map A to B. If each unit represents 15 feet, determine the distance between the nose tips of planes B and A. So that's the distance formula. Okay, so let's start for the beginning though. So they're flying in this tight diamond formation. Find the horizontal and vertical components of the translation that would map A to B. So which ones am I concerned about? A to B, right? So that's it. My focus is from A to B. All right. How am I going to find, first of all, my horizontal and vertical components? What are those? What variables would those represent? A and B. Which one's horizontal? A. Which one's vertical? B. All right. So how am I going to find my A? X sub 2 minus X sub 1. Okay? So what's my X2?
Wait, what is the X2? Is it the B?
1.3 negative.
No,
Well, I'm going from mapping A to B.
So it's, yeah, it's -5.4.
Negative 5.4 minus, what's my X sub 1? Not 1.3. Negative 1.3. All right, so what's my A then? Negative 5.4 minus negative 1.3. Nope. Because this is addition, right? Minus a negative is changed this to a positive.
Oh, yeah, that's right.
So now you really just need to subtract those. Negative 4.1. Good, Lucas. All right, so then let's find our B. If we subtracted x2 minus x1, we're going to do what with our b's? Y2, right, minus y1. So what's my y2 value? $2.8, right, because we're going from A to B, so this is my y value there, minus, what's my y value for plane A? 3.9. So B equals 2.8 minus 3.9 is negative 1.1. Perfect. What can I write from this? Once I have my A and my B, what can I write? I can write the mapping rule, but what else could I write? Not the vertex, the vector. Right, because the vector is your A comma B. So what is my vector for this one?
So it would be
Negative 4.1 and then negative 1.1.
You got it. If we wanted to write the mapping rule, we could do that. What would our mapping rule be? It doesn't say we have to, but Luke or Caden mentioned that. Do you want to write the vector, the mapping rule? Okay. So we found all the components. So we could write our vector. Now we have to determine the distance. Okay, so now we need to do the distance. 329. What do you mean 329?
That's for you to find out. And you to tell me what it means.
So,
It's that dice game.
So remember, to find the distance of the vector, okay, we have to look at the horizontal, look at it as a triangle. So this is our A is the horizontal and B is our vertical change. We said, okay, if we can use it as a right, we can use the Pythagorean theorem.
so 4.1 squared.
Well, I'm going to put negative 4.1 squared.
Is it plus what? Negative 1.1 squared? It'd just be 1.1.
Keep forgetting about the
So-
negatives.
Equals what?
16.1.
Not 16.1. Equals.
I was doing like the 4.1.
Okay, so let's finish out this equation first, though. A squared plus B squared equals
B squared.
D squared, right? To finish the Pythagorean theorem. Okay, but yes. So then this is 16 point what? No. Right, because you got to think 4.1 times 4.1. So it is 41, right? 0 placeholder, and then 4, and then, right, because 4 times 1 is 4, and then you have 16. So 16.81.
That's what I said.
But that one would be 1.1, right?
Nope, 1.1. What's 11
Oh,
times 11?
1.21.
1.21. It's 121. Okay.
You square root it.
You want to square root them.
Ugh.
You got it. So we're going to want the square root of 18. You got to round, or you got to carry. Right, 1 plus 1 is 2. 2 plus 8 is 10. So it's not 17, it's 18. So what is the square root of 18.02? You can use calculators to help you on your math.
2. Alright.
Can you give me the next number? Okay, round it to the nearest hundredth.
Just start guessing numbers, kid.
Well.
6.
What would it be to the nearest hundredth?
4.24.
It is 2.4, but if we round it, it's going to be 4.25,
5.
yeah, because it's 4. Well, actually,
That would be
it would be 4. The book says 5 because it goes, I don't know.
who do we believe?
So we'll,
Calculator or the-
Me.
I believe the calculator over the book. I'm just saying the book had 4.25. Usually I don't pay attention to it, but I remember writing that one down because I didn't have my calculator. All right, so here's the distance. But now we've got to take the next part into consideration. Which is what? If each unit represents 15 feet, determine the distance. So we have to get it to feet. How are we going to do that? So mind you, so 1 unit
81.2.
1 unit is equal to 15 feet. And we have 4.24 units.
So the top
1.2.
So we times them.
which is 63.6.
Okay, what did you times it by? Okay, why did you times it by 15 instead of dividing it? Do you remember this unit multiplier or dimensional analysis? Maybe you've talked about in science, chemistry. So if you don't, sometimes it's a struggle to know what to do if you multiply or if you divide. We've kind of talked about this before, I think, in this class. But this 1 unit to 15 feet is a unit rate. We can write it as a unit rate. In order to cancel the unit that's here, which is units, we need that same unit in the denominator. So they'll cancel, which means the other unit goes in the numerator. And then this tells you you need to do 4.24 times 15. Other times, if the setup will tell you, oh, if it's in the denominator, then you have to divide it. But does that ring a bell from science at all? Dimensional analysis?
Sadly.
Unit multipliers? Okay. So 63.6 feet or 63 point, hold on. Yeah, 7 feet, depending on how you rounded it. Did you round it for me?
No.
Okay. All right, then that's it. You can get started on your translations and using vector notation and all the craziness there.